All right, the last procedure of slices that we'll take a look at in detail by deriving equations is Spencer's method. And I'll say up front, Spencer's method does satisfy equilibrium. I'll also make the argument that we should no longer be using the ordinary method of slices or the simplified Bishop procedure. There's really just no reason for us to use methods that don't satisfy equilibrium. One problem, though, well, and then I'll also say there are many other methods that do satisfy equilibrium. Morgenstern and Price, and there's Chen and Morgenstern, a whole bunch of other ones too. One of the issues is that in order to satisfy equilibrium, we have to make a lot more iterations, and sometimes those iterations may fail to converge. So it's good to have multiple methods that do satisfy equilibrium because sometimes one will work and the other one won't. The ordinary method of slices and the simplified Bishop procedure will almost always provide you with a solution. The question is just whether that solution is valid, right? It can be pretty far off for some problems just because they don't satisfy equilibrium. All right, so what Spencer assumed was that inner slice forces were all inclined at the same angle theta. So theta is a constant for the entire problem, right? The forces acting on every single slice are inclined at the same angle theta. And what he did to simplify was to model, instead of independent slices, he modeled the resultant of those slices qi, where q is also acting at an angle theta. And in the absence of any kind of external force, like if you don't have a force acting at the top of the slice or something like that, q has to act through the base of the slice at the center because none of the other forces produce any moment, and therefore q also cannot produce moment, it has to act through the base. As soon as you have external forces, like let's say you had ponded water and there was a force acting on top of the slice, q would have to move around in order to provide equilibrium. All right, so here's a little diagram that shows the coordinate system we'll use. It's relative to the base inclination angle, z prime and x prime, and that distance right there is alpha, and then that angle right there is theta. All right, so what we'll do is sum forces in the x prime direction first, and we come up with this expression t minus w sine alpha plus q cosine alpha minus theta is equal to 0. Then we can do forces in the direction inclined perpendicular to the base and solve for n. So we get this expression right there for n. Then we compute sigma prime based on our equation for n. And then we substitute it into our expression for t, right, where we have shear strength times delta L over F. So we get this fairly long expression for big T. Then I'm going to use my algebra magic wand here with this little squiggly blue arrow, and I'm not going to bore you with all of the calculations. But what we'll do is substitute T back up in here, and we will solve for Q, right? And Q appears here and there, so it does involve a little bit of algebra. But anyway, you get this expression for Q that depends on the factor of safety, F, and it also depends on the angle of inner slice force inclination, theta. So both of those things are unknown, right? We're going to make an assumption about theta, solve the problem by iteration to where we get equilibrium based on the assumed factor of safety. So we'll do that by assuming a factor of safety, then computing the factor of safety for that theta, and iterating until those factors of safety agree. And then we'll have to also iterate on theta until we get both force and moment equilibrium for the same value of factor of safety. So it's like 2 levels of iteration that we have to do. It's a lot more complicated than either the ordinary method of slices or simplified Bishop procedure. All right, as we saw for the simplified Bishop procedure, one way of expressing equilibrium is that the sum of all of those inner slice forces has to be 0. So we're going to do that now for the the simplified Bishop procedure, sum of Qi is equal to 0. That's a force equilibrium expression for both horizontal and vertical force equilibrium. Okay, then we're also going to enforce moment equilibrium about any arbitrary point. So we have to define a datum. In this case, the datum doesn't have to be at the center of the circle. It could be anywhere. So let's say we have a datum right there at 0, 0. When you set up a problem using a program like Slide, it's going to use 0, 0 as the datum in order to solve for moment equilibrium for Spencer's method. So for each slice, like here's one of the slices we're solving, there's going to be an x coordinate of the base of the slice, x sub b, and then there's going to be a y coordinate at the line of action of q. All right, and q may or may not act at the bottom of the slice. If you have external forces acting on the slice, q will shift around. So you have to solve for yq, which is the height to the line of action of q. It's equal to yb, which would be the base height, plus the external moments divided by qi cosine of theta. So mo of I is the moments produced by all of the external forces acting on the slice. A lot of the time those are 0, so yqi would just be ybi. But, you know, again, if you have like an anchor force going through here or an external force on the top, then yqi is going to be different than ybi. All right, so here's the solution procedure. Pick a trial value of theta. We can call it theta trial, maybe. In fact, let me write that subscript in because I do use it down there at the bottom. And then compute F trial. Let's put a trial in here too. And we have to compute one F trial that gives us force equilibrium. Right, so what you'll do, you assume an F value, then you compute an F value out, and you iterate until the two F's are the same. And what that gives you is, and you iterate using the sum of Qi equals 0 equation, so that's force equilibrium. And now what you've done is solve for the factor of safety that gives you force equilibrium for that particular theta trial value. Then you have to do the same thing here, compute F trial by iteration so that you get moment equilibrium. All right, so for this particular theta trial value, you're going to get a different factor of safety in general that provides moment equilibrium. So you've computed one factor of safety that gives you force equilibrium, a different factor of safety that gives you moment equilibrium, and now you have to iterate on that value of theta trial, right? So you don't have a solution yet. You have to keep iterating until F trial is the same for both steps 2 and 3. And that's illustrated graphically here. So if you were to plot F trial versus theta trial, the shape of these lines depends somewhat on where your datum is and other things like that. But anyway, you would get one line or one curve that gives you force equilibrium. So these are all the F trial values for those theta trials that give force equilibrium. You would get another line that gives you moment equilibrium. And those two lines will cross at only a single physically meaningful value of theta, right? They're not going to cross multiple points where multiple thetas will give you the right solution. Maybe there's some imaginary thetas that would work, but we'll keep it in the real domain. And now you've got your solution point, and you've solved Spencer's method. You know theta and you know factor of safety. So this method does in fact satisfy force and moment equilibrium, but it does so at the expense of having to do these extra iterations, and it takes a little longer to run, and it will sometimes not converge, especially for cases where you have big external forces applied to the slope. It generally does converge if you're just solving a slope with no seismic body force, no big water table acting on it, no anchors. If you start adding those external forces, Spencer's method can struggle a little bit to converge sometimes. One of the outputs that you'll get from Spencer's method is called the line of thrusts. And that's basically this green line right here is showing the height of the line of action of all of those Z forces, right? So the red arrows are like the this red arrow right there would be Z1. It's acting right to left on slice 1. And then, of course, this is also Z1 acting on slice 2, and here's Z2 acting on slice 2. And you you go through all of those, and there's some line of action of those Z's. Now, that's different than the line of action of the resultant of those forces, right? Q's are generally going to act through the bottom. These are actually the lines of action of the forces themselves. And those forces will produce zero moment about the base. So they have to be oriented at a height that gives you zero moment in the case that you have no external forces acting on each slice. Now, one thing, you should always look at the line of thrusts. What you'll see is that sometimes it comes along just fine right here, and then it hits the slope and drops down like that and goes something like this. Well, what that indicates is that you have a problem. Most commonly, the line of thrust has to act within the body, right? You can't have interslice forces that are acting outside of the slices. That doesn't make any sense. So generally what happens is that you have some cohesion and you have a friction angle, but you've forgotten to include a depth of cracking. If you fail to include a depth of cracking, you start getting tension. And once the interslice forces become negative, they're not compressive anymore, that shifts the line of action outside of the free body diagram. So anytime you see a line of thrusts that goes outside the free body, you have to fix something. There's a mistake that you have to fix. Usually you have to add a tension crack zone. Okay, let's talk real quickly about some other methods. I won't go through all of the assumptions that are made in these other methods, but I wanted you to be familiar with them. There's a method by Morgenstern and Price where instead of assuming that the interslice forces all act at a constant angle, they allow that angle to vary as you go from left to right throughout your domain. So the S forces are equal to some constant times a function that's prescribed, oftentimes a harmonic function, and then times the normal forces E. So in this way, the interslice forces can vary. So what you would see is a line of thrust where maybe the forces are acting even in the opposite direction, and then they slowly kind of transition as you move through the free body. The factor of safety you get from Morgenstern and Price is almost identical to Spencer's method. In fact, as long as you use a method that satisfies all three equilibrium conditions, your factor of safety is going to be pretty much the same. And this one also does satisfy all three equilibrium conditions. The reason it might be beneficial is that because you're giving a little bit more flexibility to how those interslice forces are allowed to change angle, Morgenstern and Price method might converge for problems where Spencer's method doesn't provide a solution. So anytime you can get a converged solution from a method that satisfies all three equilibrium conditions, you're good. Then there's a modification to that method that came later by Chen and Morgenstern. And what they did was add a refinement of the Morgenstern and Price method that gave better results at the sort of the endpoints of the slice, near the toe and the head. And so it's probably even better in terms of convergence and providing a solution. Then there's another method that I'll mention that's not actually a method of slices by Sarma, 1973. And what he did was introduced an iteration scheme to find the yield acceleration. So when we do seismic slope stability, a common problem is that we want to find how much horizontal acceleration would be required to cause a slope to start moving. And maybe the slope is stable, so the factor of safety is higher than 1, but you add some amount of horizontal body force to it, and you can reduce the factor of safety to be equal to 1. And Sarma did just that. He came up with a iteration scheme that allows you to find that yield acceleration automatically. So it's kind of nice, and that's implemented in a lot of slope stability software packages. So when you go and use a program like Slide, there is a menu that allows you to pick all of the different methods of slices you want to use for a particular problem. Just be sure to always have methods that do all three equilibrium conditions. You'll use other methods in this class because the point is to learn the methods, and you want to see like how different might the factor of safety be if we do the ordinary method of slices compared with Spencer's method. But in real life, we shouldn't use ordinary method of slices or simplified Bishop procedure anymore. So keep in mind, try and get one that always satisfies all three equilibrium conditions.